Okay, everyone. So my name is Shichi Liu, and I'll be teaching this week and the next couple of weeks. All right. So today we're going to talk about static circuits. So first I'll show some results from lab 3 that hopefully you've finished last week. And then we're going to talk about some very simple basic circuits, and then we'll build up to much more complicated ones. So we start with the diode connected transistor. And then we go to current mirrors and how you would scale current mirrors. Then we move to differential pair, current correlator, bump, anti-bump circuit, then to a transconductance amplifier. And we look at transconductance, how you compute transconductance, also the gain of the amplifier itself, which is the A. And then finally, moving on to a wide range transam. Okay. So here you see sort of a small zoology of the circuits. So you see, for example, the current mirror circuits, right? The differential pair, and then below you see the current correlator and the bump anti-bump circuits. And so we're going to learn how we can design such circuits and also the transfer function of the circuits itself. And now we have a transconductance amplifier, and here's the wide range transconductance amplifier. And you see this pieces that of the circuit are composed from what you saw in the previous slides. For example, here you see a differential pair, which is highlighted in black. And then you see the current mirror at the top, right? So this is the PFET current mirror. And then for the wide range transconductance amplifier, you see again the part that's similar to the one on the left. So this is a 5 transistor transconductance amplifier, and with the wide range transconductance amplifier, you see many more current mirror circuits. So a couple more PFET current mirror circuits, and then the NFET at the bottom. Okay, so before we dive into the set of circuits, let's look at some of the results from lab 3, which is on the above threshold transistor characteristics. And so the first one is, how does the ID of a transistor operating in the linear regime of above threshold scale with VG minus VT, right? And so you have the equation of how the current would change as a function of VGS minus VT. And so if you look at this equation, you know that if you plot IDS here on the y-axis versus the VG, then you should see a straight line, right? Okay, so anyway, if you plot ID versus VG, assuming that VS is 0, then you should get the set of points. These are the ones in the circles. And then you can do a fit, right, to this set of data points. And then you get some numbers for the mobility. And hopefully you got numbers that are very close to what you see here, right? So about 300 centimeters squared per volt per second for an NFET and 100 centimeters squared per volt per second for a PFET. Right, so the NFETs have a higher mobility. Okay, so now the other experiment is how does the mobility change as a function of VG, right? And so here we have the same thing again, except now you vary VG, and then you look at what happens. So you can see as VG increases, so that means that you're going much more above threshold with more current, and then you can see the mobility starts dropping. And then the next thing is, how does the ID set scale with VG minus VT? And so this is in the regime where you operate the transistor in saturation. And the equation that governs how the current changes as a function of VGS minus VT is a squaring operation. But if you take the square root of the current, then basically this becomes now just VGS minus VT. And again, if you plot the square root of IDS as a function of VG, then you're going to get a straight line again. And you can figure out what the slope is, because the slope of this line is equals to square root of mu Cox over 2 times W over L. And again, you can then extrapolate what the mobility is if you know the W and L and the Cox. Okay, and that gives you around 400 centimeters squared per volt per second, and much more than 100 centimeters squared per volt per second. So they're kind of in the same ballpark, if you like. Okay, and then how does IDS scale with L? So again, here are a set of curves for different size transistors. So you have length of 2 up to 32. And then you measure the current that flows as a function of VDS. And you look at how the current changes as you increase VDS. So this is, again, the saturation region of the transistor. And you can see it stays almost flat, right? Especially for the longer length transistors. And if your transistor is short, then you can have short channel effects. And then you can see that the current actually increases slightly as a function of VDS. Okay, so I hope you guys got very similar curves in your labs. And then you can also compute what the early voltage is from the slides by looking at where the slope of this line hits the x-axis, right? And that's your early voltage. And if you plot that, then you can also get a curve of how the early voltage changes as a function of the transistor length. Okay, and here you can see the slope is around 16 volts per micron. Any questions? Okay, boy. I never had 4 screens in my whole life, so this is very, very interesting. Okay, so can you see, so you guys see the whiteboard, right? Just type yes.
Yes.
Okay, thanks. Okay, so here's a simple model of an inverter. So you have an NFET at the bottom. You're going to apply an input to the gate of this transistor, and then you have a current source at the top, right? And usually this is drawn as a circle with an arrow coming down. And of course, this current source can be provided from one of your measuring instruments, but can also be provided by a transistor, right? And so you just have to know where to operate the transistor then. And so then you have the VD here. And so that means now this is your input. And this would be your output, right? And so now you can try and figure out for a particular current at the top, right? What would be the place where VD would go to, right? Assuming that, yes, where would VD go to, assuming that you can sweep the input? And so what you can do is you can do this. So first, if you assume that you have a steady state input of some VG, so sorry, I'm going to actually erase this now. So assuming that VG is constant, then you're going to have another current source at the bottom, and this is ID set, right? And what you need to put in is now this extra resistor, because if you remember the curves that you get, if you plot I versus VDS for a particular VG, you get something that looks like this, right? And so if you operate this transistor in saturation, then you have to include this effect of a slope, right, to your I versus VDS curve. And so then this conductance is now reflected as a resistor. And so you say that G here, the conductance of this resistor is GD set over the voltage, okay? And so now, how do you find this point or this current, this VD voltage where both currents would equalize each other? So now this is like Kirchhoff's current law, right? So which means that for the current at the top, the sum of the currents at the bottom should be equal to current at the top. So let's call this I top. And then the current here, ID set, plus the current that flows through this resistor has to be equal to I top. And so what people do then is that usually what you can do is you plot now a picture of, let me erase this, of the current as a function of VD. Okay, let me put that my little resistor. Okay, so you have one flat line here, which is the I top, right? And then you plot this similar curve down here at the bottom, right? So if we're assuming a particular VG, then you're going to get something that goes like this. Yeah, actually, it should be more on the flat side. So let me redraw this a bit. So it should be going up, and then saturating, so maybe like that. Okay, so which means that now you can, for the steady state situation, then you know it has to be at this crossover point, right? Because then the currents at the top and at the bottom equal each other and there will be no net current, which means that the voltage VD over here won't change anymore, right? So if you have a discrepancy in the current that's coming from the top versus the current that's going out through the ID set plus the current that's going through here, then there's going to be some net current that's going to change the voltage here at VD, right? So at this particular place over here where this crossover, then you know that this is the steady state VD voltage, right? So then you know what VD is. So if this is VD1, then you know that in the end, this will be equals to VD1. Okay, so what I can do now for this circuit is I could increase the value of VG, right? I could, for example, increase by 0.1 volts. And then you know that the resulting, I don't know how to pick colors over here. So the resulting curve is going to look, it's going to go higher up and then it's going to cut over, right? And so which means now that if I look at the intercept, right, then now this is a new point, this VD2. Right, so what that means that since we increase VG to VG2, then this will be ID set 2, and for ID set 2, then your VD value will now change. So you're going to sit at a lower voltage. Okay, does that help? All right, so anyway, so that's what you can do if you want to compute where the voltage VD would sit when you have a set VG value. Okay, now let's look at the gain of the transistor. Okay, so let's go back to the thing. Okay, so what is gain? Right, so gain is the change in VD as a function of VG, right? Because that's the output, VD is the output and VG is the input, right? And so now what you can do is you can factor out into two partials, right? And so that would be the change in the current as a function of VG times the change in the drain voltage as a function of the current, okay? And so we know what that is. That is GM. That's what people call that. And then this is 1 over GD. Right? Keep on tapping. Okay, so can you write in the chat if you know what GM and GD are? Or did you learn this in any of your past 3 lectures? Yes, okay. Shem, are you answering for the whole group in the sense that you know? Or?
No, sorry, I just answered for myself.
Oh, just myself, I see. But did you encounter this in any of the lectures before? I mean, for this class. Somebody said transconductors, GM we had. Okay, GD not. Okay, all right. Okay, cool. Okay, so so GD is, so you guys didn't have this thing where GD equals to I over VE, like ID set over VE. You didn't do that? Yeah, right. That's right. GD is 1 over RD. And GD is ID set over the early voltage. Okay, so now what we can do easily is, since you know what GM and GD are, is that GM is in subthreshold anyway. It's going to be kappa. So GM is equals to kappa I over UT, right? If you don't know how to do this, just go back to the subthreshold equations of ID equals to I naught E kappa VG over UT, and you differentiate the current as a function of VG, and you're going to get GM, right? There's this one. Okay, and then for GD, again, it's I over VE, right? And so now I can plug it into this equation. Let me pick white. This is going to look messy. So this is equal to kappa I over UT times VE over I. then you can cancel out the I. So in the end, let me scoot this up. This is going to be capital VE over UT, right? And so then you can plug in the values. You can assume that kappa is 0.7, LV voltage is 100 volts, and UT is 40 millivolts. And so if you plug in the numbers, then you can get very high gain values. So in that case, as on your handouts, it's around 3,000, right? So it's huge. It's a huge change. Okay. And you can use this equation of computing the gain with GM over GD. You can also use it for the transconductance amplifier that you'll learn later. Okay. All right. Any questions? Moving on from here? No?
So excuse me. So the expression of GM is equal to kappa for E over UT works in
Kappa
general.
I over UT, yeah.
Kappa I over UT works in general or just for the subthreshold?
Only for subthreshold. Yeah,
only for
subthreshold.
Okay,
yeah.
perfect.
I think you have to derive it in the lab for above threshold this week. Yeah,
that's probably
because yeah, it's going to be much uglier. That's the nice thing about having exponentials in your current voltage equations, right? Because the above threshold equations, it's a square, so it's not going to be as pretty as this. There's going to be a square root of I in there, and also the VG will come also into the equation. Yeah, you'll see it.
Okay, thanks.
Sure. Okay, so then what we'll do next is we're going to go to the first circuit that's two transistors, right? So this is the current mirror. I think that's the way to do a forward page, isn't it? Okay. All right. So if you look at the current mirror, so from that little zoology that you saw earlier, so it's for an NFET, it looks like this. And for a PFET, right, because it's VDD, then it's like this. Okay. And so what you have here, you would have some current coming in, say I in. This could come from another transistor. And then this would be your I out, right? And then same thing here, now your current is going to come the other way. It's a current sink, right? Because the current is going down into the lower power supply, and then you have I out over here. Okay. So again, notice the arrows are different, right? So the first one, the input current is coming from the VDD power supply, if you like. And then for this one, the input current is going into the ground supply. Okay, that's why you have to choose one or the other depending on which current you are trying to mirror, whether it's going into ground or it's coming from the power supply. Okay, so now when you do the current mirror, so I can delete this one for the moment. So the current mirror is kind of sort of easy to know why it's a current mirror, because first of all, the current flowing to a transistor is a function of the gate and the source, and you can see here that the gate and the source are common to both transistors, right? And so what's the difference between them? The bulk is the same. So the only thing left is the drain voltage, right? So here the drain voltage is tied back to the gate, and here the drain voltage is sort of open. Depends on what transistors you're putting at the very top, right? And so now you know that to operate the transistors in saturation, that's the best place to be. Because in saturation, then the current doesn't depend on what this VD is doing, right? So if my VD changes, so say in a 3 volt supply, right? If my VD is going between 1 volts to 3 volts, the current here doesn't change that much, right? Because we still have to remember this curve before, where I is a function of VD, and if you're sitting at a particular VG, then it will look like this, right? So this doesn't change much, even though VD here is changing by a lot. Okay, so that means that if you use a current mirror, you have to make sure that whatever circuit that you hang on top of here will not push this voltage here below some value. So in subthreshold around 100 millivolts, right? But if you move anywhere above that, then you can be sure that the I out will be very close to I in. Okay, so first of all, because it's an input current coming in, something has to set the gate voltage, right? So you cannot do this. Sometimes people draw a circuit and then they draw this. Okay, so this circuit should look funny to you, right? Because it's true, you have an input current, you can say, well, the gate is tied to something, it's not floating, right? But the thing is, nobody's driving the gate, right? So how is this voltage here set? Okay, so easiest thing is to take a diode, right? Because we know then the gate voltage here will go to a place where this transistor will also sink I in, right? And then now, since you have the same gate voltage over here, this is in saturation, then you know that this I out will be equals to I in, of course, assuming that the sizes of the transistors are the same, and also this source voltages are the same. Okay, so then, given that it's an exponential, which is very nice always, you can then write your equations again, right? So it'd be I minus Vs, because usually you drop the Vs because they set it to ground, but you don't always have to tie the source to ground, by the way. I mean, the source to ground, right? So you'll see in a second that you don't have to do this. And it actually gives you some extra properties to the circuit. So now you tie the gate. So this is VDS over here, right? But remember that for this transistor here, the gate is equals to the drain voltage, right? Because you're tying as a diode. So that means you can rewrite this equation as 1 minus E minus D. Yes. Okay. Right. And then you can sort of sort things out, because remember, this is a kappa VG, but the kappa is not on the VS, right? It's just on the VG. And here it's really just VG and VS. So what you can do is you can lump things together, right? And you can then, let's see now, G minus S. And let's see, minus kappa G. Okay. All right. And so when VG is reasonably big, this term disappears. And so then in saturation, you get U kappa VG minus VS, right? So nice simple equation. Okay, any questions? Don't think I know how to move to the next page. All right. So for PFET, it's the same. Okay, I can't move to, I thought I would save something there. You're gonna have. Okay, so I've already drawn the PFET. And now what we're going to see is whether we can change I out. So I'm going to erase this too. We're going to see, can we make V out greater than or less than I in, right? Because I don't always want to make I out equals to I in. Right? And so one thing you can do is that, because you know that the current flowing to a transistor depends on the W or L of the transistor, even though we don't write it out, it's really part of the equation. Then what you can do is you can make a scaling between these transistors. You make it different, right? So that means that if I want, so this is 1 colon N, where the gain, which is I out over I in, is normally 1, but in this case, it's going to be N, right? So if I make the W over L of the transistor M times bigger than the transistor on the left, then I'm going to get a gain, right? So if M is say 2, then my gain will be 2. So that's the simplest way that you can make a gain. But of course that if you make the gain by changing the W or L, that means when you build the circuit, you can't change it later, right? It's just stuck at 2. And also, you'll see later on, if you take the neuromorphic 2 class, is that the if you make the gain of the if you make the size of the transistor different from the input transistor, then you have to be careful about how you actually scale this transistor or size this transistor, so you actually do get a gain of 2. But this is going a bit too much into the next class. Okay, so the second thing that you can do, which is probably nicer if you want to make a gain of 2, is to do this. Right? Actually, this is quite preferred now for the new technologies. But you always want to make multiples of a unit transistor. So again, this will be the same W or L for all the 3 transistors. But since you have 2 of them over here, then your M is really 2, right? And so your gain will be 2. So if I want M to be 3, then I would add another unit transistor, right? And then the M will be 3. Okay. So again, if you do the scaling this way, the scaling is fixed. And so once you get the chip back, you can't change it. And so usually what we want to do is, if you want to be able to play around with the gain, then you do it a different way. And so actually the circuit still looks the same, but now what you do is you're going to pretend that you have 2 different values for your source voltage. And now you're going to write the equations again. Yeah. So that means your gain now, remember, is I out over I in. And so that would be I naught E kappa Vg minus Vs1 for the first, Vs2 for the output transistor, and then it's I naught E kappa Vg minus Vs1 for the input transistor. Then of course, nicely you can cancel out a bunch of stuff. And then what you're left with is E minus Vs2 plus Vs1. Okay. If you like, it will be Vs1, Vs2. Okay, and so that's the gain of the circuit. So if I, for example, what should I do if I want a gain that is greater than 1, right? What should I do? Oh, see, now I see it's a question from Hajar. MOSFET and circuits in saturation region, both MOSFETs? Yes, they are in saturation. Okay, do we want Vs1 to be greater than Vs2 if I want to gain? Oh, thank you, Mark. Vs1 has to be greater than Vs2. Yeah, that's correct. It seems very strange, doesn't it? Because so what you can do is, because you really don't want to have 2 different voltages coming in to drive the transistor circuit, usually you have to set one of them to ground, right? So which one would you set to ground? I'm curious, actually, what you guys were saying. So we're going to set Vs1 or Vs2 to ground, but I still want a gain that's greater than 1. So which one should I set to ground? Oh, I see. Some say Vs1, some say Vs2. Some say both. That's a good one. Well, we want a gain that's greater than 1. Well, so you can look at the equation here, right? So if I want a gain that's greater than 1, then Vs1 has to be greater than Vs2, right? If I set Vs2 to ground, then Vs1 will be some voltage that's higher than ground. If I set Vs1 to ground, then Vs2 has to be negative. Right, exactly, Nicola. So which means that we don't want that case, because you don't want to have negative voltages, right? Because your power supply is from ground to VDD, right? It's all positive. So if you want to make a negative voltage, it's possible, but it's just, yeah, it's messy. So that means that you really want to tie this to ground, right? And then you would set this to a voltage that's greater than 0. Yeah, okay. All right, that's good, guys. All right, so now we're going, so knowing this, you can actually go now to the diff pair. But before I go there, did you guys learn about source followers? This is another 2 transistor circuit that's also very useful. Is that, can you put on the chat, is it a yes or no? Otherwise, I will go quickly into the source follower. Yes, okay, great. Okay, so then you know how the diff pair works if you know the source follower, right? Because the diff pair is actually has the source follower as a component of it. So here's the diff pair. It's going to be a bias current, right? IB. Should we call this VB? And this is V1 and V2, right? And the question is, if I change the voltage of V1 versus V2, then how does the current that flow through these legs change as a function of V1 versus V2? Oh, okay, you appreciate it. Okay, all right. Yeah, I'll do that in a second. Okay, and so the bias current here, if I look at just one of them, right? So we're going to do this. Yeah. So you recognize that? That's a source follower, right? Assuming that you tie this to VDD, because with a source follower, if we're talking about an NFET version of it, it's got a bias current here to set a fixed current flowing through the bottom. And then this is your output, right? And here's your input. Okay. And so if you have a fixed current over here, then you know that the output has to change. Depending on where the in sits, the output has to move to a place such that this current, you could say I top, has to be equals to IB, right? So I top has to be equals to IB. Because if I top is not equals to IB, then you're going to get a net current at this node that's going to change the voltage, right? At this node, because even though we don't draw it, there's actually a little capacitor at every node of your circuit. Okay, so it's going to move to a place where I top will be equals to IB. Okay, and this is a source follower circuit because the output follows the input, right? So if I say I stay, let's make it simple. So let's say VB is equals to 0.4 volts, right? And you know that if this has to be true, then in steady state, if I put this, say at, say I put it at a volt, right? Put V equals to 1 volt. And the question is, what is V out going to be at in steady state, right? So you can use the usual exponential equations and subthreshold, and then you'll be like I top will be equals to I naught E kappa V, what did I say, 1 volt. V in minus V out equals to IB, right? And IB I can rewrite as really what the transistor IB equation is. That's E kappa VB, right? So we know that if it's equal, then basically I can cancel both sides, and I know that kappa V in minus V out equals to kappa VB. And then if I now make a even nicer simplification, I assume that kappa is 1, right? Then basically it says V in minus V out is equals to VB, assuming that kappa equals to 1. And so that means that V in is equals to V out plus VB. So by the way, this is not absolute, right? So really I should write it. Okay, there's actually a change in V in and V out. So, but just to simplify the whole thing, to show you that it's a source follower, you can see that V in, V out is, I should flip it around actually. That should be the wrong way. So actually I should write that V out is equals to V in plus VB. Okay, so nice, a better way of showing it. So this is a follower, right? Because if V in changes, V out changes. Okay. So which means that in this particular circuit over here where I have 0.4 volts, now I know the VB, which the VGS across this transistor, right, is also the same value as the VGS across this transistor. right? Because it's the same current. So that means I should have 0.4 volts here, right? VGS, which means that this V out you can compute, right? It should be 0.6 volts, right? Because we say that V in is 1 volt. You can see the 1 volt here. Right, so 1 minus 0.4 gives you 0.6, right? If I change this in steady state, if I change this to 1.2 volts, then what is my V out? Again, this assuming all ideal scenarios. Let's see. What's the answer? 0.8. Yeah, that's right. Very good. Okay, it's not 1.6, okay? So I hope I don't get that. Okay, all right. Okay, good. All right, so that's source follower. And so you can see it over here also. There's a piece of it that looks like a source follower. Okay, now the source follower, you can imagine, is now extended so that you have another source of current flowing here to the second transistor, right? But you can again use Kirchhoff's current law, and IB is equals to I1 plus I2, right? So the current flowing out of this node is equals to sum of the currents flowing into this node. And so now you can again use the good old equations. So we say that IB is I naught E kappa VB, right? Equals to I1. And again, just initially assume everything is in saturation because that's easier. And then we're going to give this a special letter V because we need to compute VGS, right, which is here. And so that means this is I naught, E kappa V1 minus V plus I naught E kappa V2 minus V. Again, these are all the same size transistors, everything. Okay. All right. Now what can we do? So first thing is you can cancel all the I naughts, right? So it makes your life easier. And so the other thing is the only variable that you don't know is V, right? Because you're setting VB, V1, and V2, right? So that means that you have to figure out how V depends on V1, V2, and VB, right? So let's see how we can solve that. So once you drop the I naughts, right, then you have E kappa VB equals to, and then you can see E minus V is common to both these two terms. So you have E kappa, yeah, like that. Okay. And then now you can solve for EV. So let's put it on the positive side. I'm going to move it over here. So that means we have, in the end, this equation, right? So everything's okay with that? Oh no, of course kappa cannot be 1, but you know, if you want to have an intuition about a circuit, sometimes you don't want to put in all these numerical values, right? So you just, you know, you're going to assume that kappa is a constant anyway, even though it's changing as a function of gate voltage, right? But if I just want to have an idea of the functionality of the circuit and to make things easy, like, you know, is this circuit a source follower or not? I don't need to know that kappa is 0.7, right? I just want to know what that circuit's doing. And so it's just easy sometimes to just drop the kappa just to reason through the circuit. And once you can reason through the circuit, then you better put all your kappas back because you're not going to get the right current, right? It's a function of voltage. Okay. Yeah, it's just easier for intuition. Okay, so then you can compute V from here, right? So V is the log of these two things. I mean, this whole term here, which I won't write out again. Okay, and this, if you write the log, then this actually, okay, I'll write it properly. So this would be E capital V1 plus E2 minus the log. Remember, for division, when you take a log, it's a subtraction. And so this would be minus capital VB. Okay. And then if you assume that kappa, like say, for example, if you assume that V1 is greater than V2 by 100 millivolts or so, right, then you assume that most of the current is going to flow on one side. And so that means in this case, you would just drop this term off, right? Then what you get in the end is just capital V1 minus capital VB. So again, it's an assumption, right, that V1 is greater than V2 by 100 millivolts, then you can drop off one of the terms. Okay. All right, so you can actually compute what V is. And what this is saying is that V is always going to track the higher voltage, right? It's going to follow V1 in this case because V1 is greater than V2. But if somehow V2 becomes greater than V1, because that's what you can do, then V is going to follow V2. So as V2 moves up higher, V1 is going to move up along with it, assuming that you don't move V1. Okay, so say it one more time. So if I keep V1 constant and V2 is greater than V1, right, then V is going to follow V2. So if I increase V by, say, another 0.5 volts, then V will increase by approximately 0.5 volts. Okay, I don't remember again, this is like, if I say kappa is 1, that's the reason why I make kappa 1, because then it just gives you a feeling for what's going to happen. Okay, all right, any questions? All right, so now we're going to keep some of the stuff here. We're going to write out what V1 is. Try not to waste too much. Yeah. So I1, so we're going to compute I1 now. So I1 is I naught E kappa V1 minus V. Okay, remember everything has a UT below, but I'm not writing that because it looks messy. Okay, so then you can solve the equation, you can put back V. So it's, remember, you don't have V before, right? Because V is derived from the other 3 voltages. So now you have an equation here that I lost the other guy. Okay, right, you have the EV here. So you can plug this equation into here, right? And if you plug it in there, then I have to go back to red again. So that's equals to, I'll let you guys figure this out because it's just a bunch of math manipulations. But you should get this. Oh no, it's not there, right? Yes. Okay. So it's going to be I naught times E kappa V1 over E kappa V1 plus E kappa V2. Right? And of course, for I2, then you should get the opposite because, oh, sorry, actually, this should be IB, isn't it? This is IB. And so for I2, you get the same thing. So now you write I2. It's going to be IB, E kappa V2 over E kappa V1 plus E kappa V2. Okay. And then you can see that if I take I1 plus I2, then the IB comes out. Then for the numerator, you get E kappa V1 plus E kappa V2, and that will cancel out the denominator, and then you get back IB. Okay. All right. And so, so now you have the 2 equations for I versus IB. You can see it depends on V1, V2, and IB, right? The V is gone now, right? And so if you look at this equation, this is also what looks like what they call the Fermi function. Okay, can you read my handwriting? Maybe not. The Fermi function. Okay. All right. Okay, so any questions before I move on? No? All right. You can also simplify these equations if you like, right? So you say, okay, too much kappa, E kappa, something on the top and something on the bottom. So you can simplify this equation to, I keep on erasing my stuff here. Okay, so I can divide top and bottom by E kappa, sorry, this is 2 and this is I2, right? So I can divide top and bottom by E kappa V2, so that's 1 over E kappa V1. So you can make it much neater, okay, by dividing top and bottom. Okay, so now that you have this equations, then what you can do is you can plot how I1 and I2 changes as a function of V1 minus V2. So everybody has this. Erase all this stuff. Okay, so we are going to do this in your lab this week, I think, for sure. It's actually very nice to see this picture. Okay, so then here you're going to plot delta V. So just say it's V1 minus V2. And then here you're going to plot I1 and I2, right? And then now you're going to plot the curves for I1 and I2 separately. And so now you have to find the 0 point. Because what do you expect at the 0 point? So 0 point here means that V1 is equals to V2. What do you expect I1 and I2 to be? Let's see some answers in the chat. Half IB, okay. For both currents, right? Because in the end, you have to sum to IB. Okay, that's correct. So at this point over here, this will be half IB. Okay. All right, so then let's take V2. All right, so what would happen, sorry, I2. So what would happen here when I'm out here? So now here, let's say somewhere here. So remember, this is a V1 now is greater than V2 at this point, right? So do you think I2 should be half IB, 0, or some other value? Let's see. Winston, you already gave one answer. Let's see if somebody else gives a different, or gives another, somebody different gives an answer. I don't see anybody. Is everybody lost? Okay, so you think it's the higher current and don't think it's IB. So I'm talking about I2, okay? And when delta V is positive, because this is the 0 point and delta V is here, it means that V1 is greater than V2, and over here, V2 is greater than V1, okay? Yeah, it's 0. Yes, it's flipped around. Yeah, this is how it can get tripped up. Okay, all right, so that's correct. So here, you know, it's going to be 0. So you've got 1 point here and 1 point here. And you know that if you're sitting over here where V2 is much greater than V1, all the IB current is going to flow to this leg, right? And so that means, you know, there's another point here, IB, right? And of course, it's how in the world are you going from across these 3 points? Well, we know we have this exponential function, this Fermi function. And so that means that you expect then this curve. Okay. So this is I2. Okay, and then because of symmetry, then you know that if you look at I1, right, then I1 has to be the opposite because they have to sum up to IB. So that means, again, you see in the 3 points, and you're going to do this. Okay, and this is I1. So everything's good. And you can, of course, write how, if I take the difference of the two currents, I'm not going to tell you how we can do that right now, but you can, at least mathematically, you can write pick what, I1 minus I2, and then you can use the equations that you had before, the Fermi functions, and then you'll see that it's going to be E kappa E1 minus E2 for the sum of the two exponentials. And then everybody knows this is a tanh function, right? So IB. It's too slow. You guys can read this, right? Anyway, you can see in your notes. Okay. There we go. So you guys now know the transfer function of a differential pair. Yeah, it's kind of cool. Okay, let's see now. Okay, so here what I'm plotting is just I1 and I2 separately. It's not I1 minus I2, right? So that means that you have to you have to do a different plot, which of course 0 doesn't give you half IB, right? If you do that. Okay, let's see.
Yes. Which was the name of this equation again? I think I missed it.
The one with the tanh function?
Yeah.
Are you talking about the one before where we computed I1, I2, and it's IB over 1 plus E something?
No, it's just the one for the tanh function. The tanh function, I think. Yeah.
Yeah. So that's just so this is just an equation that describes the difference between the two currents as a function of V1 minus V2. So it's saying that if I change if I say keep V1 as the reference current and I move V2, right, then depending on the difference between the two currents, the two voltages, right, then the difference between the currents also changes as a function of a tanh. It looks like a tanh. So basically, if I have to redraw the curve, let me do this. So let me draw this equation here. So this will be now I1 minus I2, right? And this would be, again, V1, forget about the kappa. So it's V. Okay, so that means now with delta V, so same thing again like you have with this other curve, right? So here's the 0 point, right? Then the question is, what should it be here? What is I1 minus I2? Does anybody want to say? What is the equivalent I1 minus I2 for delta V of 0? I'm looking at the chat now. So it's going to be 0 IB. Yeah, those are all good possibilities. Okay, IVO2 could be minus IB, right? Could be many things. So easiest thing is if you take these two curves here and then you subtract them, right? So at the point here where delta V is 0, right, it's half IB for both currents. So if I subtract half IB and half IB, I get 0. So this is 0. So I got 1 point here. Then if I go to this very positive delta V voltages, then again, I can look at I1, it's IB, and if I look at I2, it's 0. So I know here it's IB, right? So I get another point over here. And then if I go this side, well, now it's actually 0 for I1 and IB for I2. So it's 0 minus IB. So this is actually minus IB. Right, so now if I draw this picture, voila. Okay, very terrible drawing. Make sure you follow a tanh function. Okay, so it's going to be like this. Yeah, is that good? I hope that's what you were looking for.
Yeah, it was. Thanks.
Okay. Sure. Okay, I think there's a pre-lab where you're going to have to do this for the above threshold operation of the transistors running in above threshold. And so it wouldn't be so bad, so don't worry so much about it. Yeah. Might look a little bit ugly, but you can do it. If not, the TA should be able to help you. Okay. And do you know how you can run the above threshold? How do I run this trend? I mean, why can I consider this as in subthreshold? Is it something to do with the voltages, the input voltages, or is it something to do with VB? Or is it a combination of all three? Or what are some common applications of diff pair? Well, it's the base of a transconductance amplifier. And since we're going to use transconductance amplifiers a lot, you'll see that it's good to know the diff pair. Okay, so to my question, so if I run this in subthreshold, if I say the circuit is running subthreshold, why is it running subthreshold? Is it because of the voltages I apply to V1, V2, or to VB? All three. Okay, Shem. So you mean all three have to be in this proper place for subthreshold operation. So, so if I say that VGS has to be, say, 0.4 volts for subthreshold operation, then can you give me some possible values for V1, V2, and VB?
Sorry, VGS off?
Mm-hmm. Yeah, for subthreshold. So I say that in subthreshold, the VGS, just I give one value only, right? Of course, it's a range of VGS values for the transistors in subthreshold, right? But let's just say it's 0.4 volts. Just pick one value only, right? So I've got three voltages that I can drive, right? V1, V2, and VB. So which transistors, which of the three voltages should I set to this 0.4 volt VGS value? I'm just curious whether you guys know why I can even consider this circuit to be in subthreshold and what makes it subthreshold, right? Because we're not talking about a single transistor, we're actually talking about a set of transistors. Okay, Vincent says VB. Okay, Jeff says VB. Yeah, that's correct, right? Because in the end, the current that flows through the circuit is dependent on VB, right? Because VB sets IB, and the two other currents that flow through the other remaining two transistors have to sum up to IB. Right? So this voltage sets whether the whole circuit is in subthreshold or not. So it doesn't matter where I set V1, V2, as long, I don't break some sort of bounds or something. I could have set V1 to 3 volts if for a 5 volt power supply. And the transistor will be considered in subthreshold only if you know what VB is. Okay, because I mean, 3 volts sounds big, right? Okay, and so to make it above threshold, then what do I do? Chaim, since you're the last person to answer. There.
So set the IB such that, set the VB such that the IB is higher, is a saturated current that flows through both the transistors.
So don't get confused about linear and saturation, because those are operating regions of a transistor. Whether you're in subthreshold or above threshold, you're always going to have these two regions, right? So if in subthreshold, there's a linear and a saturation region. If you're above threshold, you also have a linear and saturation region, right? So if you want to set it, go ahead.
We set the VB such that the VGS minus VT is about something.
Yes, right. Okay. All right. Yeah. Then you're right. Yes. And you're right in the sense that you also, even if you set VB high enough so that you know this transistor is operating above threshold. So say you set the VB to 1.2 volts, right? So clearly above threshold. Then the current that actually flows through this transistor is still dependent on the fact that you can consider this transistor to be in saturation, right? Because if this V value moves down for some reason, right? And one way to move it down is by moving this voltages down, right? Because remember, V has to follow one of the two, right? Whoever is highest. Then you could make this transistor go out of saturation, right? So it's still operating above threshold, but it's now in the linear regime. So which means that now your IB current is going to change, right? It's not going to be one constant value, but it's going to change depending on this VDS value. That drawing, okay. Depending on what VDS is of this transistor, right? Which is just V minus ground, which is V. Okay. All right, so let's move on.
I have one question. If we consider that our system is above threshold, just because of the bottom MOSFET, do we need to use above threshold equations for the MOSFET 1 and
Yes.
MOSFET 2?
Yes, exactly.
Also, the individual MOSFETs could be in sub-threshold, as we consider the whole system is above threshold, so all the equations.
Yeah, it is, okay, it's very dependent on the VGS of the transistor, right? So both V1 and V2 have a VGS that's a function of the little v, right? And so for first order analysis, I mean, it's true that one of them could go into subthreshold, but I think it's too painful to do this, right? So the easiest thing to do is you say the bottom transistor is running above threshold. I assume it's in saturation, right? Even though it might not be. But for most cases, you probably would set V1 and V2 to voltages that are high enough so that it's guaranteed that it's saturation. And then I use above threshold equations for I1 and I2.
Okay, thank you.
Yeah, right. Otherwise it's too crazy. I mean, then you should run SPICE or write some real program, right? That will bring in the right equations depending on what the currents are and what the VGS is. Okay, and then you can also write the GM. You can compute the GM of this differential pair, right? So it's no difference. It's the change in the I1 minus I2, right? I1 minus I2 as a function of V1 minus V2. And if you go and differentiate the tanh, right, then what you get is something that looks very similar to transconductance of a single transistor. It's going to be kappa IB, but it's over 2 UT. Okay, and so this GM is actually the slope of this curve over here, right? It's right here. Right, so the slope here. So that's kappa IB over 2 UT. And you can get this by differentiating this this equation, right, as a function of V1 minus V2. So it's nice that it's if you use exponentials, everything is very clean, right? It just depends on IB. You don't have any V1 minus V2 coming in, right? And so now for again strong inversion, we leave it to you to try and do this first yourself. And it's not very pretty, but let's see. Here. So the GM for above threshold is going to be beta times IB, right? And then you can recompute it, right? It's going to be square root of 2 IB over VB minus DT, right? So now you've got a square root. You don't have like just IB. So when you want to cancel out things, it's not so fun. But that's what you get for a squaring operation. Okay, so let me move on now, and we're going to talk about, well, okay, that's the current correlator. So 3320. So I'm wondering, yeah, let's do the current correlator, because I'm wondering whether I should go to let me go to the transconductance amplifier first, because it's actually an extension of of the circuit, right? So remember, we want I1 minus I2, right? So how would I do this? Does anybody have an idea? I'm going to have to add something to my circuit. Let me make this nice and clean again. What? So here's my div pair circuit. And what I want is I1 minus I2, right? So right now, you know, these transistors are dangling, right? They don't have anything above them, right? So if I tie this to VDD, I don't get I1 minus I2, right? I would get I1 and I2 changing, but that's about it. But I want something that gives me I1 minus I2. So how would I do this, you think? Oh, sorry, that's a VT, not a UT, thanks. Okay, just quickly then is take one of your circuits that you just learned, which is the current mirror, right? And then which type of current mirror should I use? Because I'm gonna have to mirror. Remember, I can subtract two currents by making one current come this way and then the other current coming this way, right? Because if I do that, then the net current here, depending on which way you show the flow of the arrow. So if I can somehow make this I1, right, then I know the net current flowing out here would be I1 minus I2, right? So now the question is, how am I going to make I1 come out here from the top? Yeah, right. So very easy. So use another circuit that you've learned, which is the PFET. So again, they have to be connected, right? Same gate voltage, same VS, right? Then you, of course, have to have the gate driven by something. We notice in exams, sometimes people don't draw what the gate's connected to, except to each other, right? So the thing that sets the gate voltage, right, you have to tie the drain to the gate, right? It's a PFET, so remember the drain is lower than the source. Okay, and if you do this, and if you assume ideal current mirror, then this should be I1 because this is I1, so where should the current flow? The only way is through this transistor, right, from the power supply. And then because it's a mirror, then this is going to be I1. Again, ideal case, right? And then the current flowing out here will be I1 minus I2. Right? And so this is your transconductance amplifier. Doesn't help me in writing. Okay, can you guys read transconductance amplifier? Okay. Right, and sometimes we call it a 5-transistor transconductance amplifier because you can actually make it quite complicated. Like yeah, but this is the simplest one that you can use. Okay, any questions? So if I measure, you know, I1 minus I2 using the circuit, then I'm going to get this IV curve that I showed here on the right. Okay. There's kind of little non-idealities that if I go into it, it actually takes some bit of reasoning. But the first thing I guess I just want to mention here is, first of all, this circuit's not going to be perfect, right? If you actually look at the textbook, you'll see why it's not perfect. And, you know, ideally you want this voltage here. If I'm going to use this voltage, say, right, then I want it to be able to swing from 0 to VDD, right? That would be nice if you could. And so the first thing is, do you think you can go towards VDD? This node here. Oh yeah, another thing I want to point out is actually this is a combination of not just a source follower, but if you like, this actually looks like an inverter circuit. So now this output here, let me call it I out, okay? And then if you Okay, so you have two things. You have I1 minus I2, and you can also have V out, okay, right? And V out is going to go to some place so that Kirchhoff's current law is obeyed. Right? So let's assume, first of all, that V1 is much greater than V2, right? So then the current flowing through these two legs, right, it has to be IB, but because V1 is greater than V2, we can say the current's flowing through here. In fact, you can say everything's flowing through here, so this is almost close to IB, right? You might get some little current through here, but you should say it's mostly here. Then this would be IB, yeah, which means that you're going to have some gate voltage that would give you IB on this side. But because this current now is very tiny, then what do you think is going to happen to V out? So you have a net current that's close to IB, right? So I1 minus I2 is close to IB. So this current is going to charge up this node here, right? Because again, imagine there's a little capacitor. And I'm going to go and dump charge on the capacitor. And so that means this voltage is going to go up, 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 up. At some point, as this voltage goes up, remember this transistor operates in the saturation region only if it's, just remember the I was this VDS curve. So if VDS starts going backwards, because I out is increasing, right? So that means your VDS is going back this way. Which means at some point, you're no longer getting IB here, but you're getting smaller and smaller currents. Yeah. And you're going to stop when the current through here, which is no longer IB anymore, it's going to be much less than IB. So when this current here is equals to I2. Do you guys get it? Yeah, so if it gets near VDD, doesn't it make the PMOS above triode? You mean it makes the PMOS operate in the triode region, right? And that's true. Close to IB. No, that means the current now will be close to 0. Right, so this mirror is not going to work like a current mirror, actually. Yeah, right. Yeah. So that means I out is not I in, but this I out is actually close to 0. Okay, and that's because this transistor is no longer in saturation. And so that means your V out can be close to VDD, right? But it cannot be like right at VDD, but it can be close to VDD. So now the difficulty is that let's go the other way, right? So let's now assume that V2 is much greater than V1. So here, when you make it the other way, you actually run into a very interesting problem, which takes a bit of thinking of, and so probably might take some time for this to sink in. Which means like after the lecture even. Okay, so that means that instead of I2 now, you can say that this is, what the heck? This is IB, right? This is close to 0. Not draw anything. So this current here is close to 0, which means that this current here is also close to 0, which means that your I1 minus I2 is now negative, which means that current's actually going in this way, right? Which is good because that means that now what should happen is that V out should decrease, right? Because now your current is going out this way, right? So I'm actually discharging the capacitor. So now my V out is going to drop, and of course you hope that it drops to ground, right? Ideally you want the full swing, but you cannot drop it to ground, right? So why can't you drop it to ground? Why can't I discharge this below, all the way to ground? Here I can charge it up all the way to VDD, right? But now when I make V2 greater than V1, I actually cannot bring this all the way down to ground. You guys see why? Kind of interesting. It involves the little v, right? Something we can, this little v over here. Because V2 cannot conduct any current through M2. Yeah, right. So it's actually very strange, right? Because right now the current is flowing this way, right? And that's because V is less than V2. But then, so then if you now have, say, V over, so let's say this is close to ground, right? So that's actually kind of a strange thing, because what does this mean? It means that now my VDS, my drain and source are flipped around, right? Because this voltage will be at a lower voltage than the V, right? So that means that it actually implies that the current is flowing this way, right? It's a bit weird to think of this V out as being able to drop so that it's lower than V, because it can't do it, right? That means now current is going this way, and of course current is not going this way, right? Current is actually coming this way. And so what this means is that your V out cannot drop below the V, right? So I leave this for you to think about, and then we can speak about it more next time. Sounds weird, right? So, and we know that V follows the higher of V1 or V2, which means that this V out, the lowest V out that you get to, is also going to depend on what the values are of V2 and V1. And this is what we call, if you have the book, it's called the V-min problem. So you can look in the textbook, but this is called the V-min problem. Right, so V out cannot drop all the way to ground. It would drop to a minimum voltage that's dependent on V1 and V2. And so because of that, this is voltage, this node here is not so great if you want to use it as an input voltage, right? Because it's not, first of all, it's not going to go to ground completely. And then second, where it goes to depends on where you set V1 and V2, right? So what we're going to do now is we're going to change this 5 transistor transconductance amplifier circuit to something that's called a wide range transconductance amplifier circuit. So let's delete all this. We'll redraw everything. So here's my diff pair, my 2 input voltages, my current mirror, but now we're not going to put a current mirror because we're going for a output voltage, a node where the output voltage can swing all the way. So what you do here now is you mirror both sides. Right, so before, remember, we tied these 2 PFETs so that they're one current mirror, but now you're actually going to create 2 current mirrors right from here. So here's one of them. So this is I2. This will also be I2. Now I'm going to mirror out this side. Right, so this is I1. Now to follow this one, I1. Okay, and then remember, in the end, you always want I1 minus I2, right? Or I2 minus I1. In this case, that's what's going to be. Okay, so that means how do you do that? Again, because the current's now flowing the same direction, you have to flip the sign of one of them, right? So you get the minus. So the easiest way to flip is to add a current mirror, right? So now you need an NFET current mirror. So this is I1. And now your current is flipped around, right? So remember, this is going from VDD and this is going into ground. Okay, so it's think of this as now the negative sign. And so now if I take the output from here, right, now this would be I2 minus I1. So you probably should flip the signs here. So okay, I'm going to make it consistent. Okay, so we're gonna make I1 here, I1 here. And this will be now, as usual, I1 minus I2. Okay, and so now you see this output voltage here is not dependent on anything below it, right? It's just a P-FET and an N-FET, right? So which means that this output voltage can now swing almost over the whole power supply range, right? So again, you're gonna have some constraint on how far up Vout can reach towards VDD, and you get the same thing on the other side, right? You'll reach almost close to ground, and it's not gonna have this Vmin problem. And this is what we call the wide range transconductance amplifier. So it depends on what circuit comes after it. It doesn't mean that you should always replace all your five transistor conductance amplifier with the circuit. Right? Depends on what you're doing with the output of this amplifier circuit. So, okay, any questions? Nothing in the chat? Everybody good? All right. Yeah, once you learn all these little different building blocks, it's actually kind of fun because you can create your own circuits, right? If you kind of have to just consider all the things, is it a sub-threshold? And if it is, then are you making assumptions which break down because the voltages move out of range or the currents move out of range? Yeah. Okay, so I think the final circuit that I should go into is the bump circuit and the current correlator circuit, right? I think you do have a current correlator exercise this week. So what's a current correlator circuit? So one of the functions that's used a lot in this neuromorphic circuits is looking for similarity between two input currents, sometimes also between two input voltages. And this is a current mode circuit, so which means that the inputs and outputs are all in terms of currents. And the simplest way you can make a current correlator circuit is, if I say, is I in 1 similar to I in 2, right? So again, you guys know about current mirrors now. So what you can do is you can mirror I in 1, right? There's an NFET here, and then I can mirror I in 2. Again, there's an NFET here, but now what we're going to do is we're going to stick this output NFET on top of the first one, right? And now this is my I out. Okay. Everybody okay with that? So very, very nice compact circuit, okay? And so now you can go through and you can write the equations for this. And again, to know that, again, you have to always look to see whether somebody's in saturation or not in saturation kind of thing. So in this case here, for this, so let's call this M1 and M2, so that's similar to your notes. So this transistor here is not in saturation, right? Because this voltage here is going to be determined by the VGS needed to put out I in 2. So very likely this is not going to be in saturation. Okay, so what it means then is you have to write out the full equation. And so this equation has to be the same flowing through. So if this is I out, this has to be I out, and this has to be I out, right? So that means you write the first equation for I out for M1, which is I naught E kappa V1 1 minus a little, what's it called here? V? Yeah, it's a little V here. Okay. Okay, let's do the other way. So that's not. Yeah. Okay, and then now I have to write the same thing for M2, and I'm going to assume that it's in saturation. So that means my other equation for I out is going to be I naught E kappa V2 minus V. So I need to write 2 here and 1 here. Okay, so far so good. Okay, then you can solve for the e to the v again. You have 2 equations here with 1 unknown, so you can solve what it should be. And so as a function of so I naught v, put that over here. So e kappa v2, is that correct? Yeah, that's correct. Okay, so then I take this equation, the second one here, and I can solve for EV. And then what I'm going to do is I'm going to put EV back in here, okay? Back into the first equation. I'm going to substitute back in again. And then I'm also going to write I1. I'm going to represent I1 as I naught E kappa V1 and I2 as I naught E kappa V2. And then if I substitute in here, so let's see if it works. I naught is equals to I1 times 1 minus E kappa V2. So that's I2 over I out. Right. Wait, it's not quite right, is it? Oh wait, this is totally off, man. Okay, this is not right at all. This is correct. So that's I out. So if I take I out over here, then that gives me I out squared. So it's I1, I out minus I2. So that's not quite right. I think there's a mistake somewhere. Okay, let's not waste any time right now. I have a feeling one of this equation has a flip sign. But what you should get in the end is that I out is equals to I1 times I2 over I1 plus I2. Okay, so what it means is that if I1 is equals to I2, right, then you know it's going to be, say, I1 squared over 2I1, so it's like a half of I1. And then if I1 or I2 is greater, then, so say I2, let's look at this equation. So if I2 is greater than I1, much greater than I1, then what you're going to get for I out is I1 times I2 over I2, cancel out, and you're going to get I1. Right. And if I1 is much greater than I2, then again, you cancel out and I1 is equals to I2. Okay. So, so basically it's saying that if I could plot, what's current correlator says is that if I plot I out versus I1, see which one should it be? If I plot I out versus I1 minus I2, yeah, so how similar it is. So then I should get a peak here, right? Because when I1 and I2 are similar, then I get the biggest I out. And then if any one of them is bigger than the other, like a lot bigger, then my I out should drop off, right? Because the I out is always the smaller one of the 2 input currents, right? So then you get like a little bump, right? Like that's where we're going to the bump anti-bump circuit, right? So this tells you how similar 2 currents are. You guys got that? Kind of went around a little bit rambly. Any questions? No? All right. Could you repeat what common mode means? Okay, I didn't talk about common mode, but is this in regards to the differential pair circuit? Daniel?
I think you mentioned it when you started talking about the current correlator, but maybe I heard it wrong acoustically. I'm not sure.
Ah, okay. Yeah, no, I didn't talk about common mode. Common mode is actually something that you consider when you have the differential pair circuit, right? Because what you the IV equations that we show, it's current versus delta V, right? V1 minus V2, right? So it doesn't say anything about what that actual DC is. It's saying that, okay, you know, I could have, so if I have V1 minus V2 at 0.2 volts, I could have put V1 at 1 volt and V2 at 1.2 volts. I could have put V1 at 0.5 volts, right? And V2 at 0.7 volts. I mean, both cases, the delta V is 0.2 volts, right? But the common mode is different for the two cases, right? So one of them is like 1 volt, or actually it should be 1 plus delta V over 2, right? The other one is 0.5 or so. And so it doesn't look like the common mode voltage matters in the equation, but it really actually does matter overall, because in a differential pair, remember the little v. So this is actually getting away from your current correlator right now. Remember, in the differential pair, there's that common voltage, right? The little v. And this v here depends on the common mode voltage of V1 and V2, right? So if you move V1 and V2 down, 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 right, then the V is also going to follow. And if the V gets too close to ground, then this transistor will go out of saturation, right? So the equation applies most of the time, but if your common mode voltage is too low, then the equation again changes. Okay.
Thank you.
Yeah, but yeah, sure. All right. So now for the bump, anti-bump, it's using these pieces of the current correlator, and all you do again is like the diff pair. Yeah. Right. So you recognize this part here, right? That's the current correlator circuit that you just saw. And the only thing you did was to add a current at the bottom, the tail current, right? We call it the tail current also, by the way. So we added this part over here so that we can limit how much I out can be, right? Because in this case now, I out will be, the max it could ever be is close to IB, right? And so you can, again, of course, if you like, you can put a diode at the top if you just want to get the current from here, right? I put some diode and I can tap out the gate voltage and use the gate voltage to drive another transistor somewhere to get this I out. And so this gives you the similarity current. But since I have this other two legs, right? If I could sum up their current, I should get the opposite, because now everything has to sum to IB, right? So this current here, which is the current that measures the similarity, has to, if I sum it with the two blue currents, that actually measures the dissimilarity. So they both have to, all three of them, I should say, have to sum up to IB. So you can now, if you take this, it'll be ugly. So you can somehow join them up and have another transistor, right, that provides the sum of these two currents, right? Then this current here would be your I of your dissimilar current, if you like. I dissimilarity. Okay, or we call it the anti-bump, right? So essentially what it means that you've got the one curve here, where you have this, right? So say, let's just say it's V1 minus V2. This is your I out, right? So this is your similarity current. And then you have the other one here, which is going to look like this. And we call it the anti-bump. So let me change this back to be consistent, right? So this is the anti-bump current. And this would be your bump current. Okay. And again, you can use the same equations that I show here, except now you use Kirchhoff's current law, and you can derive what the output is. If you can get it, then ask the TA, or we can go over it next time. But the I out in the end is going to be IB over my. I'm just writing straight from the slides here. Cosh squared of kappa delta V over UT. And so the
excuse
yes,
me.
yeah.
I think I missed something. Which one in the circuit is the anti-bump current?
The anti-bump. Yeah, the anti-bump current is the one that I drew in blue. This guy's.
Okay, and it's also IB. So
no, it's not IB. They have to
okay.
sum together. The similarity, the bump and anti-bump have to sum up in the end to IB. Right. So if
okay.
You got it? Yeah. So actually, let me do this. I just show you the picture. I think it might be easier. Because there's some measurements done from, there you go. See that? So again, you have the two transistors, V1 and V2. You see my mouse, right? And then you have the current correlated circuit, the I1, I2 plus I mid sum up to IB. Yeah? And then you can see.
Okay.
Huh?
Yeah.
Yes?
Yeah.
Yeah, it's good.
Okay.
All right.
So I1 is the anti-bump with the I2, I think.
Yes, I1 and I2 are anti-bump, right? But it depends on which one is bigger, V1 or V2 is bigger. And then I mid is the bump circuit, if you like. The one that measures the similarity, right? How close, how similar you are. So it's high when you're the same. And then you, then you drop off as you go away. And so now you see the green curve and then the blue curve, right, for the anti-bump, and then you get the red curve for the bump.
Okay.
Is that good?
Thank you.
Yeah. Yeah, I mean, you do. Yes. You do use that quite a bit, right, in different ways in your morphic circuits, right? You might want to measure like the voltage of some circuit is close to some reference circuit that you care about. And if it's too far away, you want to, say, imagine it could be in a control loop, right? If it's too far away from the reference voltage, then you want to have a current that flows that does something, right, to make that voltage close to reference current, right? And then when it's close together, you might not want to change things anymore, right? So that's how it's been used over the years. Yeah, I mean, there's sort of interesting things that go with it. For example, you don't size all the transistors to be exactly the same, right? So it turns out that there's this S factor that you can define, which is the W or L of the middle transistors versus the outer transistors, right? And from measurements that were done, at least for transistors that were fabricated in old technology, you want to make this S greater than 1, which means you want to make this middle transistors larger. And that's a reason for this, but it goes deeper into the device physics. If you guys are interested, when Toby teaches again, you can ask him these detailed questions, because he was the one who came up with the circuit. And he did a whole bunch of measurements on different circuits that have different S's, right? So basically similar copies of this circuit, but S here, for example, would be 32 times bigger than the outer ones and so on. And then you can see the effects on how it changes this curve over here. Yeah, it's quite interesting. Okay, and then hopefully you can get these equations, right, from the current correlated equations. So you should get that I out is this. So this is the bump equation, right? It's IB. That's the max you'll get. And then it's 1/4 S is the scaling factor times the cosh of delta V over 2UT. So you recognize this kappa delta V or 2UT. Also was in the equations for the transconductance amplifier, right? Except there was the tanh kappa delta V over 2UT. Okay, and then you can get the anti-bump, that's I1 plus I2, and that's just IB minus I out. So if you know what I out is, then you can compute what I1 plus I2 is. And then you can also write out the minimum I1 plus I2 that you're going to get, and turns out that it actually depends on the scaling factors, because you can see now the S comes into play here. Okay. And I hope you you learn some cool circuits that you can use in the future. Remember, this lecture is static circuits, right? So static circuit means steady state. I change something, I wait long enough till the circuit goes into steady state, and then I measure what that resulting changes on input, on the output currents or the voltages, whatever not. So these are not transient circuits. No, I mean, sorry, I shouldn't say they're circuits still, but we're not looking at the transient effects, right? So if I do like a step function, I change the input voltage, you know, say from 1 volt to 1.2 volts, I'm not showing you what happens to how the output voltage or the current changes as a function of time, right? This is a thing that we're not looking at yet. So we start simple static circuits, 2 transistors, to 5 transistors, and if you can get this, then you're in a good place. Okay, and then we'll make it harder and harder as time goes on. I shouldn't say harder, more complex and more interesting. All right, guys. See you next week.
Thanks. See you next week.
See you. If you have questions, yeah, write to me.